In this tutorial, we'll walk through how to generate a beam lattice ramp based on the results of a stress analysis. Because the model itself is fully parametric, adjusting the beam's length regenerates the entire process, from the analysis all the way to the ramp. Even when you change conditions such as the load, the shape re-optimizes right away. First, to define the dimensions of our beam, we create two number sliders, one for the x length and one for the yz length. To build the beam's volume from these dimensions, we feed both sliders into a domain box node. To create a box shape, we add a BoxProp node. To define the faces where our supports and loads will act, we place a YZ plane at each end of the beam and build a rectangle on each plane. Then we add two mesh plane nodes, generating a mesh on each face. Now we have two planes ready for the loads and supports. To anchor one end of the beam, we use a fixed BC node on the left face mesh, locking all three axes. To apply a load on the opposite end, we add a force BC node and drive its direction with a unit Z node pointing downward. To preview where the supports and forces act, we connect both into an implicit BC display node, showing the fixed face and the force arrows in the viewport. When you want to feed multiple outputs into a single input, hold the Shift key while connecting the nodes. To build the ramp shape we'll actually optimize, we start a new branch with an implicit box, then add a rectangular cell map to divide it into lattice cells. To fill those cells with a lattice, we use an implicit beam node, tiling a cubic beam structure across the cell map. Now, since the goal of this tutorial is to adjust the beam's radius based on the analysis results, from here, we'll compute the stress analysis and feed it back into the ramp. To bundle everything the solver needs, we use a merge node, combining an isotropic material set to steel with our fixed and force boundary conditions. To run the analysis, we add an implicit static stress solver, which outputs displacement, stress, von Mises stress, strain, and distance fields. To visualize the results, we connect an analysis display node, then switch its field from displacement to Mises stress to see where the beam is most stressed. We can confirm that the analysis ran without any problems. To feed the stress back into our geometry, we add a field select node and pick the Mises stress field. To normalize that field into a usable range, we use a bounds node to find its minimum and maximum, then pass it through a remap numbers node. This remaps the stress values to a range between 0 and 1, To turn the normalized stress into a thickness driver, we add an implicit ramp and wire its output into the implicit beam's beam radius input. Now, the struts grow thicker where stress is high and thinner where it's low. To control the thickness range, we tune the implicit ramp's outmin and outmax values, shrinking the minimum strut radius for a finer lattice. Because the model itself is fully parametric, adjusting the beam's length regenerates the entire process, from the analysis all the way to the ramp. Even when you change conditions such as the load, the shape re-optimizes right away. In this example, we tuned a beam ramp, but the same approach works with a TPMS lattice. You can drive the wall thickness of the gyroid from the analysis results in exactly the same way.